transformation with homogeneous coordinate. Three transformation with coordinate. So three-dimensional transformation with each other any point with three dimensions x, y, and z. For Homogeneous coordinate, we use another one that we call it as x. Correct? It is written as x, y, z, and x. Correct? X dash, y dash, z dash. X, where x dash is equal to x x, correct? X dash is equal to x x. If x is equal to 1, multiply with this or with 1. If x is equal to 2, multiply with all. Y dash is equal to x y and z dash is equal to s z. Why do we need homogeneous coordinate? Because without homogeneous coordinate, if we perform any transformation, it is no origin only. If we want to transform the origin also, we use the homogeneous coordinate concept. We are using that and going to see all 3D transformation one by one with examples. Before start with the all 3D transformations such as calculation scaling, first we see the general transformation matrix. So what is the size of general transformation matrix here? The size of general transformation matrix is here now 4 by 4. Why? Because there are 4 coordinates x, y, z, and x is there. So the general transformation matrix that we have seen previously is 3 by 3. In normal, it is 3 by 3. But we add one coordinate, homogeneous coordinate, and now that's why the general transformation matrix, when we consider the homogeneous coordinate, 3D transformation with homogeneous coordinate is 4 by 4. So I'm going to write it here, the transformation matrix C. This is standard general transformation matrix for 3D transformation homogeneous coordinate. So here A, B, C, D, E, F, G, H is not used. H is used for homogeneous coordinate. I, J, L, M, N, and these are P, Q, R, S. Now every this 4 into 4 matrix, it is divided into 1, 3, 4 matrices. So that I am going to write here. This general 4 into 4 matrix, transformation matrix, has 4 parts, partitioned into 4 parts. Partitioned into 4 parts. So that I am going to write it here. So upper 3 by 3, lower 1 by 3, lower left, upper left 3 by 3, lower left 1 by 3, upper right 3 by 1, and this is 1 by 1. This is 1 by 1. So I am showing here with this diagram or this. This is upper left 3 by 3. Okay, this one upper left 3 by 3. A, B, C, D, E, F, G, I, J. Then this is lower left 1 by 3. and this is upper right 3 by 1, 0, 1 product, and this S is lower right 1 by 1. So this 4 into 4 general calculation divided into this 4 partitioned into these 4 parts. Now these 4 parts what is indicated? So this upper left 3 by 3 matrix. This upper left 3 by 3 matrix. What purpose it is used? It is used for all the purposes. Local scaling, shearing, rotation, and reflection. The upper left 3 by 3 matrix. This is used for local scaling, shearing, rotation, and reflection. Now, what is this lower left? Lower left 1 by 3. 1 row, 3 columns are there. L, M, N. This is used for translation purpose. This is used for translation purpose. This is indicate the values Tx, Ty, and Tk. How we want to translate the feature object in x direction, y direction, and z direction. That is Tx, Ty, and Tz values. These are represented with this lower left 1 by 3. Okay. Now this PQR. This is for perspective transformation. Upper right 3 into 1. It is for perspective transformation. What is that? We are going to study in detail. Perspective transformation. And the last remaining lower right 1 by 1. This one lower right 1 by 1. The value is S. This is used for overall scaling. This is used for overall scaling. So local scaling and overall scaling. Here we are going to see this example. Local scaling means we can scale with different values. X, Y, Z may be any value, not necessarily equal value. Okay, we can scale with any value of X, Y, and Z. That is local scaling. And overall scaling, S, means we can directly double, directly triple the object, or we can directly compress it 1/2, 1/3, etc. Overall scaling of the object. Clear? So local scaling means we can change the value X, Y, and Z. Any value, not necessarily equal. Equal scaling not necessary. But overall scaling means directly double the object, directly triple the size of the object, or minimize it with 1/2, 1/3, or any value. But overall entire object is scaled. Either it is expanded or it is compressed. That is overall scaling. And this 1 by 1 lower right matrix is used for overall scaling. This general transformation matrix 4 into 4, it is used for 3D transformation. So for translation, here for translation, here which part is used? The lower left 1 by 3 matrix is used for translation. For translation, these are LMN values. In some books or on internet, you can see Tx, Ty, Tz. Any variable we can use there. Here it is LMN is used. So here is equal to the result that we are going to get with this. The original point, one point I have written here. One single row. What is indicated What is indicate? This is a single point in 3D towards the x direction, y direction and z direction. For example, here it is in 3D, not here, but it is a single point. If we want to show the line, what we require is two rows. Okay, x1, x1, y1, z1, x2, y2, z2. If we triangle, three. If for rectangle, if a cube, how many points are required for a cube? 8 points are required, correct? Because 8 vertices is not there for a cube. For each vertex, x, y, z will be there. So for a cube, how many rows we require here? 8 rows we require here. And we are going to see this example. Now, x, y, z1, what is it? It is a single point in the 3D space. Y direction and z direction. Okay. So here it is x, y, z, and the transformation matrix is Tx, Ty, and Tz, or you can say Lm and the lower left value. In some it is given as Tx, Ty, and Tz. The values to which we are going to come. Lm or Tx, Ty, and Tz. So it is equal to x dash I dash z dash is equal to, if we multiply this point, which is a infinity with this transformation matrix, what is the result? Multiply this row with this one. It is x plus ts, correct? That is our first point, first result. Second point is y plus ty, z plus tz. If we multiply the 3D points, 3D objects with the transformation matrix, then we will get this result: x plus ts, y plus ty, and z plus tz. Means if a point in this place here something, and if we want to transform it with this ts, ty, and tz, then x is added with ts, y is added with ty, and z is added with tz. Then it may suppose transform here. Depends upon the one of the example. So in this way, see one example. Along the example, a point has a coordinate. In x, y, z direction, 5, 6, 7. And we want to translate it with the values tx is equal to 3, ty is equal to 3, and tz is equal to 2. And tz is equal to 2. We have given the point in x, y, z. Which values? X direction 2, y direction 6, and z direction 7. By writing in this format, the result is equal to 5, 6, 7. One is indicate the homogeneous coordinate. Multiply with the transformation matrix. 1, 0, 0, 0, 0, 1, 0, 0. What is tx, ty, tz? 3, 3, and 2. So 3, 3, 2, 1. Now multiply this with this transformation matrix. What result we will get here? X plus ts, y plus ty, and z plus tz. And at last, the homogeneous coordinate 1 is 1. So it is 8, 9, 9, 8991. Correct? Here, this point 5671, it is translated with new point 8991. It is translated and the new points are 8991. 899 is the expired date coordinates of the new point. Here, that is simple translation. If you want to change the object, it may be a triangle, it may be cube. Normally, to be usually three dimensions. So if it is a cube, you need to add all the rows with here C1 and C2. According to the cube, it is the position of one plane one in the place of one position one. This is the one position one. That is about the next one is rotation. We need to specify the angle of rotation. What is the angle normally? It is theta, the angle of rotation, and also the axis of rotation. Do we want to rotate to x-axis, y-axis, or z-axis? So in this way, here along with the angle theta, we need to specify whether we want to rotate to x-axis, y-axis, or z-axis. Both values we need to give for the rotation of an object. So here we require the angle or theta to which we want to rotate and the axis. Again, there are three transformation methods. One was rotation to x-axis, rotation to y-axis, and rotation to z-axis. That part already we have seen here in simple introduction to 3D transformation. Rotation to x-axis, rotation to z-axis, and rotation to y-axis. So same matrix, whatever here, the same transformation matrix. Only what we are going to add here, the homogeneous coordinate. Only we are going to add here the homogeneous coordinate. Rotation to x-axis. So when we perform the rotation about the x-axis, x remains as it is. Only y and z, cos theta, sin theta, minus sin theta, cos theta. So same transformation matrix I write here. P is equal to x. There is no change in the x coordinate. Cos theta, sin theta. Minus sin theta, cos theta, and about the homogeneous coordinate. The upper left 3 by 3 matrix, it is used for rotation. Upper left 3 by 3 matrix used for rotation. And this matrix already we have it as to x-axis. X remains as it is. Y cos theta, sin theta, z minus sin theta, cos theta. Now how to write the homogeneous coordinate? That already we have seen in 2D. How to write it for that? The homogeneous coordinate value. So that when we multiply any object, the point of any object, it is 1. And that's why it is the same value. Similarly, write down the rotation about y-axis The transformation matrix. When we talk of the rotation about y-axis, y and for x and z we have that cos theta, sin theta, minus sin theta, cos theta. And homogeneous coordinate 0, 0, 0. How it comes? Already we have seen. Only I have written as it is T3 by 3 matrix. The last rotation about this. This is rotation to some angle theta with subaxis. The angle theta is to be standard angle 90 degrees, 180 degrees, 230 degrees. The values of cos theta sin theta 1 minus 1 0 in this way. If it is a cos 90, it's a 0. If it is a sin 90, it's 1. But the angle is different other than this standard angle. We need to calculate the value of cos theta and sin theta with the help of calculator. Okay. Now we are going to give one example here. The rotation of cube. Rectangular parallel pipe RPC, or it is a cube like this. This example now we are going to see. Here the cube is given. This cube suppose our x cube, and this also rotated 90 degrees to x axis and rotation 90 degrees to y. If we want to rotate it, this is the transformation matrix for x axis rotation and y axis rotation. Consider the rectangular parallel line fiber. What we call it is the rectangular parallel fiber RPC. So what is the second given here? And it is a cube. 8 values are there. It is a 3 by 8 matrix along with the homogeneous coordinate as 1 1 1. rotate by theta is equal to minus 90 degrees. Theta is equal to minus 90 about x. So here we need to multiply it with the transformation. So the transformation matrix, when we rotate to x-axis, we need this transformation matrix. Where cos theta means cos 90 sin 90 minus sin 90 and cos 90. So cos 90 is 0 and sin 90 is 1. So it's a 0, 1, minus 1 and 0. So putting that value here and write the transformation matrix. So I directly write here x bar is equal to this one multiply with the transformation matrix C. Cos 90 0 then minus 1 so it is nothing but x multiplied with C. The final result is it takes some time to calculate. So I'm going to write it here directly the result. What is your observation? What is your observation? Here that observe this x coordinate and this x coordinate. Both are same. But because we rotate to remaining, then we change this by remaining value. So the result will be look like this. If we rotate to 90 degrees, if we rotate to 90 degrees, minus 90 degrees, it is a minus 90. If we rotate to minus 20 degrees to x-axis, then this cube will be appear like this. This will be 90 degrees. This minus 90. It is like this, but after rotation, it looks like minus 90. Similarly, if we rotate it to plus 90 y, if we rotate it plus 90 y, theta is equal to 90 degrees y. Then if we perform this multiply with the transformation matrix C, it is 0 0 minus 1 0 to y-axis. So y is a sensitive change in the x-axis coordinate. So the result is 1 0 0 1 1 0 minus 3 1 1 2 minus 3 1 1 0 1 0 0 minus 3 1 0 2 minus 3 1. So you observe here that
three-dimensional scaling. So scaling, for which purpose we are using scaling? Scaling is used for the transformation which produce scale, means enlarge or either compress or change the size. Not only enlarge or compress, it also change the size of the object. So when we consider the transformation matrix, which part of this matrix is used for scaling? Local scaling. Upper left 3 into 1 matrix is used for scaling. We require three factors for scaling: Sx, Sy and Sz. Sx for x direction scaling, y for Sy for y direction scaling, and z for Sz for z direction scaling. So that diagonal terms are used upper left 3 into 1 matrix. Diagonal terms are used for scaling purpose, diagonal only. So first we are going to see the example of local scaling, and the transformation matrix for this, normally it is diagonal terms or upper left 1 into 3 matrix is used. So A, the remaining terms are 0, 0, 0, A, B, C, D, E, correct? F, then G, I, J, correct? A, B, C, D, E, F, G, I, J. H is not used. H is used for homogeneous coordinate, and remaining L, M, N are also 0. So that is the transformation matrix for the local scaling. So in this we use the diagonal terms A, E and J. So when we perform or multiply it with X multiply with this T, the result is multiply the X with T, then in that case it is, suppose our coordinates are X, Y, Z and the homogeneous coordinate 1. A single point we consider, position, single position vector we consider here. So X, Y, Z is our X, suppose. So multiply this X with this transformation matrix. What is the result? X multiply with A. So I write AX. Then second one is EY. Third one is JZ and 1. That is the result. Means the first coordinate is multiply with A. We normally, or in some situations, some books, it is given as Sx, Sy and Sz. That is also given. Scaling in X direction, Y direction and Z direction. So X multiply with Sx, scaling in X direction, scaling in Y direction and scaling in Z direction. That is about the one position vector of the object. If how many position vectors are there? All are multiplied with Sx, Sy and Sz to scale the object. Now see it with example. Now consider the same rectangle parallel RPP, parallel piped. I write here directly the object value 0, 0, 1, 1, 2, 0, 1, 1, 2, 3, 1, 1, 0, 3, 1, 1, 0, 0, 0, 1, A, B, C, D, E, 2, 0, 0, 1, 2, 3, 0, 1 and 0, 3, 0, 1. Okay, suppose this is our X, original position vector or the object, and we want to scale, perform a local scaling with the scale factors. Sx is equal to 1 by 2, Sy is equal to 1 by 3 and Sz is equal to 1. That is the value of A, E and J. A, E and J. So our transformation matrix, I write here the transformation matrix, the diagonal terms we put that values. So it is 1/2, 0, 0, 0, 0, 1/3, 0, 0, then 0, 0, 1, 0, 0, 0, 0, 1. and multiply this with these position vectors with the homogeneous coordinates. 8 position vectors are there. So first position vector multiply with this one. I write it in your x multiply with t to get the final result. So the result is multiply this one with this one as we perform the normal multiplication of matrix. Okay, so the result is shown here in this diagram. This is our original position vector, okay, or this original cube. How it comes? That 0, 0, 0, sorry, E is 0, 0, 0, it is 2, 0, 0, 1 in this way. So that A, B, C, D, E, F, G, H, this cube, if we perform this scaling, the result is here, it is shown. It is the result that the x coordinate 1/3 we scale, y coordinate 1/2 we scale, and z coordinate remains as it is because it is multiplied with 1. That's why z coordinate remains as it is. So that is the result. Next, we consider another overall scaling. Overall scaling. Now, overall scaling, which matrix or which simple matrix is used in the entire transformation matrix? 1 into 1 lower right S. The last one is used as a overall scaling factor. So I write here it is like this: x multiply with t. X may be any coordinate x, y, z, 1, and the transformation matrix is correct. The last one, 1 into 1 lower right 1 into 1 matrix is used for overall scaling. So it is S, and this value we consider as a scaling factor. Now when we multiply this with this one, what is the result? X, Y, Z and S. Correct? The result is X, Y, Z and S. Whether it generates the scaling? No, it is not generate the scaling. Only instead of H here, the scaling factor comes. Instead of homogeneous coordinate, here the scaling factor comes. Means it is not the final position vector result. Correct? It is not the final position vector. So here we need to generate the final physical position vectors. See, once again I am telling, when we perform this kind of multiplication, it gives the result x, y, z and s. Means the first 3 coordinates remains as it is. Only h becomes scaling factor s. Means it is not the final result or final scaling, overall scaling. So for that we need to generate the scaling factor of this one h. We need to use here to perform the or to find out the physical position vector. So you can write here the physical coordinates are Then how to find out these physical coordinates? The physical coordinates are x star, y star, z star 1 is equal to. Now we want h as a 1. So what we need to do here? We want h as a 1. So what we need to do here? We need to divide all this with this s value. Then only it becomes 1. So here x divided by s, y, or I write here x dash, y dash, z dash, s, and it becomes 1. S divided by s1. So to get the original or physical coordinates, position vector, final result, what we need to do here? We need to divide the previous x, y, z, whatever the result, by s. Clear? Now see with example, then it will be clear. So write down the example. Uniform scaling if we want to perform, or double the, we want to double the object. To double the object, that is uniform scaling, overall scaling. Here the s is equal to, what is the value of s? It is 1/2. Now see how with example. S is equal to 1/2. We required here to double that particular object. To scale it double size, we require s is equal to 1/2. Now see with example. Suppose we consider x dash. I directly write here the position vectors of the object. The previous one as it is we are going to consider. In this example, whatever the result is here, that result we are going to scale it, make it double. So I write that values here 0, 0, 1, 1. Okay, so here this is the object that we want to double it. For that, what we use here, s is equal to 1/2. The transformation matrix is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1/2. Okay, now multiply it with this. What happens? See the result. As we know that x dash, y dash, z dash is same as x, y, z. I write it here again for your x dash is equal to x, y dash is equal to y, and z dash is equal to z. Remains as it is. Okay. The result is that the first three coordinates remains as it is, because I multiply this with the remains as it is. The first three coordinates. So 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0, 0. Okay. Now what is about the fourth coordinate? What is about the fourth coordinate, or we call it as a homogeneous coordinate? So what is that value here? It is s. It is s. Correct? So we multiply this one with 1 divided by 2. So it is 1 divided by 2. So I write here it is 0.5, or you can write 1 divided by 2. Correct? So is this the final result? No. Why? Because the homogeneous coordinate value is here 1/2 and we want it 1. So what we need to do it? We need to divide these values by 1/2. We divide these values by 1/2. So I write it in the next one. You can write down this. The homogeneous coordinate factor. The homogeneous coordinate factor for each of the transform position vector, the homogeneous coordinate factor for each of the transformed position vector is 0.5 or 1/2. 0.5 or 1/2. Thus, to obtain the physical coordinates, each position vector must be divided by 1/2. Okay, to find the position vector or physical coordinates of the position vector, we need to divide it by 1/2. So the previous one, this one, divide it by 1/2 and get the result. Try to find out 0 divided 1/2, 0. 0 divided by 1/2, 0. 1 divided by 1/2, it is 2. So wherever it is 1, it becomes 2 automatically. So I write here the final result, that is x star is equal to and 0.5 divided by 0.5. So all the homogeneous coordinates automatically become 1. It is our final result, and this is with this. So this is final result. This one, we scale it double. So what is our observation here? If we want to expand or we want to increase the size, what is the value of S? If S is less than 1, then expansion occurs. And if S is greater than 1, then compression occurs with the object. Opposite. As we consider the local scaling, overall scaling is opposite. For expansion, S should be less than 1, and for compression, S should be greater than 1. So opposite values we need to use. Overall scaling and local scaling. Next, 3D shearing. So shearing means slanting the object. Shearing means slanting the object in X, Y or Z direction. For shearing, we use off-diagonal terms. Off-diagonal term of upper left 1 into 3 is 3 into 1. 3 into 3, sorry. Upper left 3 into 3 matrix of diagonal terms are used. Diagonal terms are used previously for scaling. For shearing, off diagonal terms are used. So the transformation matrix is like this. Diagonal terms 1 as it is, and the off diagonal terms are used. So A, B, C, then D, E, F, G, I, 1. Okay. So here the off diagonal terms are used. The diagonals are 1 and off diagonals are used, that is B, C, D, F, G and I. These off diagonal terms are used for shearing. So the result, when we multiply it with X, which is position vector X, Y, Z, 1, X multiply with T. So Try to find out the result. This one multiply with this one. X, Y, Z 1 multiply with 1DG 0. So it is X plus Y B plus Z G first term. Next one is BX plus Y plus IZ. Next one is CX plus FY plus Z and then 1. That is the result of shearing, slanting in X, Y or Z direction. Off diagonal terms are used. So when it is slanting in X direction, Y and Z terms are used. And when slanting with the Y direction, we want use X and Z terms. And when this Z direction multiply with X and Y. That is a simple method of shearing. So the example here, consider a cube. I directly write here the cube and transformation matrix. The same cube is used here. And the shearing is factors the result is, I have already calculated. I am going to write here the direct values 0.5, 111, 1.5, 0.15, 1.25, 1, 0.75, 1.15, 1.95, 1. Okay, that is the result. This one cube, this object is shared in this. So you can observe this E as it is 0, 0, 0, 1. Only it is shared like this, slant like this. Clear to everyone? So these all are basic things we have studied about the 2D shearing and also about the 3D shearing. Okay, we have seen all 3D transformation with homogeneous. First we have seen only simple without homogeneous coordinate, all the formulas for translation, rotation, reflection, shearing and scaling. Then we have seen the 3D transformation with homogeneous coordinate, that is again translation, rotation, reflection, combined rotation, then scaling, local scaling, overall scaling and the shearing. Okay, so the next one is multiple transformation. So this part also we have seen related to the 2D part. Multiple transformation means that if we are performing multiple transformations one by one, such as translation, 2 or 3, rotation, reflection, shearing, multiple transformation, if we want to perform on the same object, then in that case, the first thing is, first we need to find out the First, we need to find out the transformation matrix. Okay. For example, if we perform the translation, then T1, then rotation, then reflection, or whatever. Rotation through x-axis, rotation through y-axis. So multiple transformation, successive transformation can be combined or concatenated. So we can concatenate all these transformation matrix together as a T. First, perform the multiplication of all these transformation matrix and then multiply it with the original position vectors or the object position vector x, and then we will get the result. But here, as we know that the matrix multiplication is non-commutative, for that the order of the application is important. We cannot change the order of this T1, T2, T3, T4. First, we perform the multiplication of T1 with T2, then the result is multiplied with T3, then the result is multiplied with T4. We cannot change the order. Why? Because the matrix multiplication is non-commutative. A in multiply with B is not equal to B multiplied with A. And that's why we need to consider this thing every time when we perform the multiple transformations. Now see, example we are going to see here. Consider the effect of translation. We are going to perform the translation with x, y, z direction, -1, -1, -1. So the Tx, Ty and Tz. Tx, Ty and Tz -1, -1, -1. That is our the first transformation matrix. Then followed by the successive plus 30-degree rotation about the x-axis. Means first we require Tr, the translation matrix with the value Tx, Ty, Tz -1, -1, -1. Then we perform the rotation with plus 30 degree in x-axis and then plus 45 degree about the y-axis. So we require another rotation transformation matrix plus 45 degree with y-axis. On the homogeneous coordinate 3, 2, 1, 1, the entire object only a single point is given here. Single point is given here. So that you need to perform. So do it on your own. Try for it. Okay. So the first transformation matrix is 1, 0, 0, 0, and these terms are used. Well, m, n, which is -1, -1, -1. Then through x-axis and rotation through y-axis. So simply here the first all multiplications are done and this is the final result. And after in this the values put are L is equal to -1, M is equal to -1, N is equal to -1, then theta is equal to plus 30 and phi is equal to plus 45 degree. Putting this value, the next result will be this one. So the position vectors given, what are the position vectors given here? 3, 2, 1, 1. Multiply this with the result. From where it is taken, putting the value L is equal to -1, M is equal to -1, N is equal to -1, 30 degree and 45 degree. This transformation matrix, which is concatenated. All three transformation matrices are concatenated or combined, and these are multiplied with the position vector, and this will be the result. And this is our final result. Suppose we perform it in different way. What is the another way? That the original position vector, it is first multiplied with translation matrix -1, -1, -1. This is the intermediate result. Then this intermediate result is multiplied with rotation 30 degree x-axis, and this is the second intermediate result. Then this intermediate result is multiplied with the third rotation matrix, this is R1, R2, 45 degree with y-axis. And this is the result. Now observe this result and this result. Both are same. So multiple transformation you can perform in both ways. First, find out all transformation matrices, concatenate them, combine them together and multiply with the original position vector. You will get the final result, or perform one by one steps. First transformation, second transformation, third transformation, and both the result must be same. Any one way you can use to perform the multiple transformation, but the order of the transformation we cannot change. The order must be same. That is about the multiple transformation.